Good evening. Welcome to day 2 of 5 days ATAL FDP on quantum computing with artificial intelligence, convergence and applications. Today we are having a eminent research person, Professor Naresh Kumar Nagwani. Sir is working in NIT in Raipur as a professor in computer science and engineering department. He has vast experience around hundreds of his research papers are in Scopus with good citations. 1131 citations are there. 131 documents were loaded with a good H index of 17 H index. Sir, we are fortunate to have you as our resource person for the day 2 session 1. We warmly welcome you to sir. Now you can take over the session, sir.
Thank you, sir. Thank you. So, am I audible, sir?
Yes, sir, you are audible. And
Yeah.
Just give me 1 minute. I'm stopping my sharing. Now you can start sharing your screen, sir.
Yeah. Yes, sir. Yes. I'm just doing it, sir.
Yes.
My screen is visible, sir.
Yes, sir, your screen is visible.
Yeah. So, presentation is also visible.
Yes, sir, it is. Yes, sir, it is visible.
Okay. Okay. Thank you, sir. Thank you for the feedback. So, first of all, thank you for giving me the opportunity to present my experience in the field of quantum computing. Um, Here, actually, I have been assigned the topic of discussing about two popular algorithms of quantum computing. Number one is Jozsa algorithm, and second algorithm is the Grover search algorithm. So both of these algorithms are quite older in the field of quantum computing. Even it is the 3 decades almost when these two algorithms have been proposed in the field of quantum computing. And there is a specific purpose that why this particular two algorithms are presented in the domain of quantum computing. Until date, we are always starting the quantum algorithm with the help of these 2 3 algorithms actually. So I always say that there are 4 basic foundation algorithms of the quantum computing. First is the Deutsch algorithm, second is Jozsa algorithm, third is Grover search algorithm, and fourth is the Shor's factorization algorithm. So suppose anyone wanted to understand about the basic quantum computing algorithms, then he has to start from these 4 algorithms first of all. So before proceeding with this particular technology, the quantum algorithm, this two algorithm, I just wanted to put a foundation that how this two algorithms came into the existence and what is the philosophy behind it. What is the concept? Why these algorithms are still the benchmark algorithms in the domain of quantum computing actually. So first of all, when we have the sufficient processing units with us, we have the high-end GPUs available these days with us, then certainly there is a question that what is the need of quantum computing? What is the need of quantum computers? And why everyone is talking about the quantum computers these days? And it is also leading to the another question like why government of India has launched the mission, National Quantum Mission, and why they have been highlighted few of the topics where most of the scientists are now focusing. So the answer is, which is shown in this particular slide, that is the quantum computers have enormous power of performing the operation simultaneously. The parallel processing can be done very effectively with the help of quantum computers. So generally, the purpose of any algorithm, any computer algorithm, is to solve any given function x. And x stands for data, input data, which is related to the algorithm. The moment we are going to increase the size of the data, like in case of AI projects, in case of data science projects, basically which is totally dependent upon the historical data. So when the size of data is increasing, we definitely need some high-end computing units by which the data can be processed efficiently. So here the quantum computers are playing a major role because the basic nature of quantum computing is to provide the parallel implementation of the code actually. And why it is possible that the basic nature of quantum computer is it is providing parallel processing. That is the fundamental of quantum computer is qubit, actually quantum bit, where one bit of quantum information is the superposition of qubit 0 and qubit 1. It means there are two simultaneous state for the given quantum information actually. So we are going to understand here that, what is the utility of this and how it is going to help in achieving the faster execution of the code with the help of two algorithms. But before that, if we can talk about the historical development of the algorithm, right? If you are a computer science engineer and you know that how the algorithms came into the existence, how the computers have started processing any kind of algorithm. So for those particular models, the basic technology is the Turing machine, which is called as the PTM, probabilistic Turing machine. And that was given a long back by the scientists Church and Turing there, where they have mentioned that it is a PTM can efficiently simulate any realistic model of the computing. It means whatever problem we have that is solvable with the help of computer systems actually. Although there are few classifications of the algorithms, some problems can be solved efficiently with the help of computers. Some cannot be efficiently solved with the help of computers, and we need the high-end computing units. So basically, for those particular set of problems, we are focusing with the quantum computing. Now, when we talk about the algorithms of computer, so we say that we can solve any problem with the help of computer algorithms, provided the computer algorithm is efficient. Now, how we can say that one of the algorithm is efficient or inefficient? So basically, that all depends upon our computing resources actually. And basically, if you are a computer science guy, you must be knowing that the time complexity is one of the parameter by which we are judging whether the given algorithm is better or not. So there is a famous problem called as the factoring problem, where given the big number like 51 is the smaller number, for example, we know that the factor of that number is 3 and 17. And when we work with the cryptographic kind of thing, or when we work with the hashing kind of things, then the computation becomes very, very complex for those cases. So for given any n bit number, suppose we wanted to factorize it with the help of classical computers, then you can see the time complexity of that, right? It is big O of small k and then to the power cube root of n, where n is the number of bits for the number actually. It means suppose I'll increase the size of bits for the number will be increased, the big number is there, the complexity will be more higher for factorization of that actually, right? So this kind of problems are still a challenging problem in the domain of computer science. In other words, this slide is only indicating that till date there are so many other problems which cannot be solved with the existing classical computers efficiently actually, right? So one of the example of such problem is factoring actually. And when I think somebody is going to cover the topic Shor's factorization algorithm in tomorrow's session, then possibly you will understand about what is factoring and what is the utility of it, how it is becoming one of the threat to the existing security mechanisms of the banking, internet, railway, and all that, right? So this is one of the example problem where we are simply demonstrating that problems like factoring cannot be solved efficiently with the existing classical algorithms. So in other words, if it is not able to solve with the help of classical computers, so is it like we can never solve that problems with the help of computers? We can solve it, but finding the efficient algorithm is one of the challenging area actually. Whereas when the computers were developed, it was claimed that the computers can solve any kind of realistic problem by the probabilistic Turing machines, which is the foundation technology of development of the computers, right? So it is violation actually. So here comes the quantum computer actually. So for us today, it is the trending technology. Everyone is talking about Quantum Valley in Amravati, right? That the first quantum valley is set up in Amravati, Andhra Pradesh, something like that. But if you can see the theory in 1980s, the foundation of quantum computers was laid down, and it was derived from the quantum mechanics subject. So there they are talking about, that it is possible to create the quantum computers on the basis of, Church Turing thesis, probabilities Turing machine, and which can simulate the entire classical computing devices into the quantum one, right? So that we are going to talk actually. And this was the biggest question in the earlier days, that whether the quantum computers are realistic. So, long back, I'm telling you one story that when I was doing my MTech, So we had a subject quantum computing in my curriculum in 2003. So at that time we used to discuss that whether quantum computers are existing or not. But today we can practically see that IBM, Microsoft, Google, everyone has launched their own quantum computers actually. So answer to this particular question is yes, that quantum computers are realistic, and now slowly many of the IT companies are also launching it actually, right? So now we are hoping that most of the problems, whatever we can solve with the help of classical computers, that can be solved with the help of quantum computers also. This slide is very important actually, and it is indicating that what is the basic power of quantum computing devices. The power is it can perform the parallel operations simultaneously. As I mentioned you that in quantum computing, the basic information is one qubit, one quantum bit, which is the superposition of qubit 0 and qubit 1. So in ordinary computing, we can perform either work on either 0 or on the 1 bit actually. Whereas when we perform any operation on the quantum computing, simultaneously that is performed on the combination of qubit 0 and qubit 1. So we have another diagram where it is clearly visible. So if you can see this two diagrams actually, one diagram is on top and other diagram is on bottom. So on the top diagram, it is indicating that it is indicating about the working of a one qubit quantum computer. So there are two diagrams again on the left hand side and on the right hand side, right? So in classical computers, information can be either 0 bit, or it can be either 1 bit. Whereas the quantum computer, you can see it is A cat 0 plus B cat 1. So it is the superposition of qubit 0 and qubit 1. So suppose I wanted to implement any function on this bit information, then independently it is applied to 0 and 1 in case of classical computer. Whereas in case of quantum computers, when we are applying the function, simultaneously it is applied to both qubit 0 and qubit 1. On the right hand side on the top, you can see this one actually. So this diagram is indicating that in the quantum computers, simultaneously one operation can perform two operations. So parallel processing is in the basic nature of the quantum computers. This is for the one qubit quantum computers. When we go for the two qubit quantum computers, then there are four combinations actually. It is superposition of four information. So classical system with two bit is something like this. We have the four combinations 00, 01, 10, and 11, right? That is our 2-bit system in the classical computers. Suppose I wanted to apply any function on this. So independently that is applied to 00, 01, 10, and 11. So four operations are required in the classical computers having 2 bits. Whereas if I can create a quantum computer consisting of 2 qubits, then my qubit can be represented as the superposition of four informations like this. It is A, then qubit 00, then B qubit 01, then C qubit 10, and D qubit 11. And the moment I can apply any function on it, then simultaneously that function can be applied to the four informations in parallel actually. So instead of my four number of operations in the classical computers, now it is carried out with the help of only one operation in the quantum computers. So it is about the two particular qubits. Suppose my qubits are 3, then I have 8 information in the classical computers, 8 operations are required. Whereas 8 operations simultaneously can be executed by a quantum computer. Just imagine that, we have 1000 qubit system, what IBM has recently launched. It means we can perform 2 to the power 1000, those many operations simultaneously in the quantum computer with the help of one operation only. So this is how that is exponential faster computer as compared to our classical computer. Even the thousands of GPU will be failed in front of a single 500 qubit system. This is how quantum computers are very, very fast. They can perform parallel processing like anything, and nothing is faster than quantum computers as of now in this world. And this is how we are only talking about the quantum computing, their power, their utility, how we can talk about the quantum computing, what are the applications of quantum computing, how it can help the machine learning, those kind of topics mostly we are discussing. Now, there are so many algorithms which are proven algorithm and which can simply demonstrate that the utility of quantum computers. So one problem which we have discussed earlier, which is quite complicated for the classical computers, is the integer factorization problem. Now, if you know about this security system, cryptography system, where our data is secured actually. So RSA algorithm, RSA cryptography is one of the very popular algorithm. And if you can recall that particular algorithm, the step number one in that particular algorithm is to compute the value of n, where n is equal to p into q, where both p and q are the large prime numbers actually. And from this n, now we are deriving the encryption, decryption kind of thing, and we are making our data secure, right? So suppose anyone can just find out that for the given value of n, what are the values of p and q? Very easily they can decode the information, and even our entire cryptography system can be cracked, right? So that is the main problem actually. So classical computers, as of now, it is not possible for them to crack this kind of thing. Whereas if we have the quantum computers, then very easily we can identify the factors of the bigger prime numbers, and that can become threat to the security systems. Now, how we can stop our security system from the quantum computers attack? So for that, we need to understand about the quantum computing algorithms of it, and then how we are going to, protect our data from the quantum attacks. So quantum cryptography is the another set of subjects we need to understand for that, right? Apart from this, if you can compare the performance of complexity between the classical computers and quantum computers. So these are the two complicated problems which takes a lot of time in the classical computers, but that can be, very easily computed on the quantum computers. You can see the differences. For the classical one, here it is in the exponential order, whereas here you can see it is simply e to the power o log of n. So very much simplified actually. It is taking few days in classical computers, whereas it is taking few hours in the quantum computers. So this is how the quantum computers are providing very excellent way by which we can perform the execution of data very fastly. Now I am coming to the actual topic, what I have to cover in the today's session. So I have to cover two basic algorithms of the quantum computers. Number one is Jozsa algorithm, which is nothing but the extension of Deutsch algorithm actually. And then Grover search algorithm we are going to talk. And possibly at the end, I will show you that, how we can implement both of these algorithms in Google Colab with the help of technologies like Qiskit or Pennylen that we are going to talk at the end. So we have to understand the working of Jozsa algorithm, right? So, but before that, we have to just understand about the basic architecture of the algorithm, right? So Jozsa algorithm solves a particular problem. What is that problem? So here I have created my, simplified handwritten notes, which I used to teach to my students. That Jozsa algorithm, solves the problem of identifying whether the function is constant or balanced. We will understand that what is function constant and what is function balanced, but it is solving that particular problem. And it is the extension of the Deutsch algorithm, right? It is called as the Jozsa algorithm. So what is the difference between Deutsch algorithm and Jozsa algorithm? That is shown here. That the Deutsch algorithm here you can see it is working on the one qubit actually, 0 and 1. And we are getting one qubit output, 0 or 1. Whereas if you can talk about the Jozsa algorithm, it is actually working on the n qubit system. We have the 0 and 1 combination n times, and it is producing a single qubit output actually. So when we say that the given function is constant or given function is balanced, where the n number of qubits are input. So this is the example in this particular table, which is indicating about the constant functions. So input is n qubit size, right? Input is consisting of n number of bits, you can say in quantum computers. So we have different combinations. We have 2 to the power n combinations of the input. So suppose x is my input here, right? And I have n number of bits as input. So all zeros n number of times that I have as the first input, and then all ones I have the last input, and in between I have the combination of 0 and 1. Here you can see. So likewise, we can say that we can have 2 to the power n combinations of input available when we have n number of bits available. So suppose n is 2, right? If n is 2, then I am having 2 to the power n combinations of input like 0, 0, 0, 1, 1, 0, 1, 1. 2 to the power 2 is 4. If n is 3, then I am having 8 number of combinations starting from 0, 0, 0, 0, 0, 1 to 1, 1, 1. So that is, our decimal value 0 to 7, total 8 values. If it is in general n bits, so I am having all 0 n number of times. then n minus 1 zeros 1, then 1 0 1 1 up to all n number of 1 bits actually. Suppose this is my input x and I'm computing any function fx and I'm getting all the output, all the values as 0, or if I am getting all the values as 1, then this particular function is called as the constant function. What is the purpose of this algorithm, Deuce-Jozsa algorithm? Once again, we can just go there and we'll find out. So the purpose of Deuce-Jozsa algorithm is to identify whether the function is constant or balanced. So now we understand that what is the meaning of constant function. A constant function is always creating the constant output for the any input, irrespective of the input, always the output is constant. So either the constant zero function can be there, which can produce all the zeros, or the constant one function can be there as the output, which produces one always actually. This is the first category of the functions, constant functions. So Deuce-Jozsa algorithm can identify given the function is constant or balanced. Now let us talk about the balanced one. What is balanced function actually, right? So a balanced function is the function which produces 0 or 1 for half of the data actually. For half of the inputs, the output is 0, and for remaining half of the inputs, the output is 1 actually. And it is not necessary that the input is in some order. Input can be any random thing, but for half of the input, the output is 0, and for remaining half of the input, the output is 1. So then we say that that particular function is balanced one. Now the question is, suppose I don't have any quantum computer, I have the classical computer, and I wanted to know that whether the given function is constant or balanced. So what we can do? So we will be taking all the inputs one at a time. We will be giving it to the classical computer. So all zeros, I can give it to my computer. I'll check what is the output. All n minus 1 times it is 0, only 1. What is the output? Then 1 0 1 1, like that I'll be testing for each individual input. So there are 2 to the power n combinations of input, and always I'll be checking for the output. If I'm getting 0 always, so 2 to the power n operations I have to perform actually. So if n is 5, then 2 to the power 5, 32 operations I'll perform. Then only I can say that my given function is constant or balanced. Or even, for identifying of the balance, at least half of the operation plus 1 I have to do actually. Then only I can say whether the given function is balanced or constant. Now, with the help of Deuce-Jozsa algorithm, we are going to say that we can check whether the given function is balanced or constant with the help of only one operation actually. So instead of doing thousands of the operation when n is higher, with the help of only one operation, we can identify whether the given function is balanced or constant, right? So we need to now talk about the algorithm Deuce-Jozsa. And this is the circuit diagram of the Deuce-Jozsa algorithm. Now, friends, before going for this particular circuit, we need to understand about the general circuit in the quantum computer actually, right? So we are saying quantum algorithms. So quantum algorithms are always represented with the help of the quantum circuits. And a quantum circuit is made out of the quantum gates actually, right? So before this, let us talk about a simplified circuit in the quantum computer, which is the simplified version. I'll show you. If we can understand this basic circuit of the quantum computer, then very easily we can understand the complicated circuits also. So this is called as the circuit of the general oracle function of the quantum computer. It is a 2-qubit input circuit and corresponding output is there actually, right? Now we are talking about how the quantum computers are made, how the algorithms are made. Algorithm is nothing but the circuit. Circuit is made up of the quantum gates. So this is indicating one kind of algorithm or one quantum circuit. Both are the same things here, which is indicating the working of the general function actually. So if you really wanted to understand about these two algorithms or other algorithms of quantum algorithms, then there are few prerequisite topics you must be aware of. And out of that, you need to understand about the entanglement theory, the quantum gates. There are so many quantum gates available for the quantum circuits like single qubit gate or multiple qubit gates. If you are understanding those gates, then only you can understand about these circuits and these algorithms. Otherwise, if you are not comfortable with those particular topics, then at least theory you understand so that later on, after this FDP or so, you can start afresh from the scratch, and then you can understand the basic foundation of this algorithms, and then you work on the algorithms. So I'm trying to simplify the entire thing, and I'm giving you the very basic things required to understand the Jozsa algorithm, right? So this is my general, function represented as the quantum circuit or quantum algorithm. So it is having two inputs, X and Y. Both are the quantum bits actually. And it is producing the X as it is output, and another one is it is producing the output as Y XOR operation FX. XOR is one of the Boolean operation where the output is 1 if the bits are different. If both of the bits are same, right? If it is 1 1, then the output is 0. Otherwise, it is always 1 actually, right? 0 0 it is 0, 0 1 it is 1, 1 0 is 1, 1 1 is 0. This is how this operation performs. Now we need to understand that how we can simplify this expression. If you are going to study quantum algorithms or quantum circuit from any book, then you will see that it is mentioning a lot of mathematics and then it is writing the generalized form. So this slide is simply indicating that how we can create the generalized form of any circuit actually. So suppose this is my given function, given circuit, and I'm going to apply one unitary function UF on this particular input X and Y. Now I'm mentioning a specific term here as unitary function because all the operation in the quantum computers are unitary in nature. And every function can be described with the help of a matrix. So matrix has to be unitary in nature actually, right? So here we are going to apply unitary function with the qubits X and Y, and it is the corresponding output we are getting. Now suppose my second qubit is minus qubit. Now I hope that you are aware of the qubit systems. It is qubit 0, qubit 1, qubit plus, qubit minus. So qubit plus is nothing but it is the superposition of 0 and 1 in the positive phase, and minus is the phase in the negative direction. So there is a gate called as the Hadamard gate, right? If we can apply Hadamard gate to the qubit 0, then we are going to get the qubit plus as the output. And again, if we can apply Hadamard over the plus, we are again going to get the 0 as the return qubit actually. This is how these gates are reversible in nature actually, right? So let us see that how general expression we can create from this particular thing, this particular function. So here you can see that suppose y is minus, then what will happen is my input will become like this. I'm going to apply unitary function on x and minus. Then here you can see it is unitary f on x, and minus is represented as 1 by root 2, 0 minus 1. Now this constant value I'm keeping in front 1 by root 2, and then I'm going to apply u of x on x, and then this 0 will come and this particular one will come into the place. Then this is unitary f x and 0, unitary f x and 1. So what output it is producing in general, x and y, it is producing x as it is, and then y XOR fx. So here you can see it will become 0 XOR fx, and it will become 1 XOR fx because my second qubit is 0 and 1 in this particular expression. Now out of this, we can just keep this constant value qubit 0 as common, and then our expression will be simplified like this. But before this, when we do 0 XOR fx, the output is always fx because 0 XOR 0 is 0, 0 XOR 1 is always 1. So we can write that expression as it is 0 XOR fx is fx. When we do XOR with qubit 1, it
Tal.
always gives us as the complement of the fx. 1 XOR 0 is 1, it is 0. 1 XOR 0 is 1 actually. It is complement of the second information. So now we keep this particular thing as common. So my simplified expression will become like this, right? 1 by root 2 qubit x fx minus complement of fx. Now there are two possibilities that my fx is 0 or fx is 1. If I'll write my fx is 0 and I can simplify this, then it will convert to the same thing as the input. It is x and minus. And if it is 1, I'll keep the value of 1 here. So complement of 1 will become 0. So it will be converted to minus x and minus sign actually. So these two equations I can get with the help of fx and 0 and 1, right? So out of these two equations A and B, if I can apply a little mathematics, my generalized expression will become like this. Unitary operator on x and minus is minus 1 to the power fx, x and minus 1. When fx is 0, minus 1 to the power 0 will become plus 1. If this thing is 1, fx is 1, then minus 1 to the power 1 will become minus 1 actually. This is how my expression will become generalized. And here you can see that my entire circuit can be represented like a mathematical formulation here, which is called as the general representation of any function. Now, friends, when you are going to understand about any quantum algorithms, so like this, there are so many expressions you need to understand because those equations are the standard equations in quantum computing, which are derived from the quantum mechanics. So if you are afraid that you know how this expression came or something like that, those are available in any of the books actually. But if you are not able to understand about this, you have to start from zero actually, because that is the prerequisite thing to understand about the quantum algorithms, right? When we talk about the implementation, there are so many ways by which it can be implemented. But for theory, for research purpose, if you are writing research papers, then definitely you have to understand about these expressions. Now, moving back to the Jozsa algorithm now, right? Here you can see that just like we have seen a general circuit of the common function, for Jozsa expression, we have this particular circuit. This is our, circuit of the Jozsa algorithm. Or in other words, circuit is nothing but the algorithm, right? So I can say it is my algorithm for Jozsa. So input, you can see it is n qubit input. So 0 we are supplying as n number of times. You can see 0 tensor product n number of time is indicating 0 is supplied n number of times. Then it is indicating Hadamard operation is applied n number of times. Then we have the unitary function actually, which is the oracle of Jozsa. And then again we are applying Hadamard n number of times. And then finally we are doing a measurement operator to identify whether the given function is balanced or constant, right? So here you can see that I have different stages for this particular algorithm, right? So it is starting from the input. Input is represented as psi 0. Psi is the standard notation for the qubit actually. So it is my input. Then when I'm applying operation number 1, that is Hadamard n number of times, that is becoming psi 1. The output is changing to psi 1. Then we are applying unitary operator, and then my output is changing to psi 2. Then again we are applying Hadamard n number of times, so output is changing to psi 3. And finally here we can see that we are applying the measurement operator, and we are able to measure about the outcome of the algorithm. And very easily we can identify whether the given function is balanced or constant. I think there are few comments here. Is there any problem?
Hello, sir. I have one question.
Yeah.
Yes, sir. Is there any other condition except constant or balanced after the measurement? There is only one. There is only two results after the measurement.
Yes.
It it
Madam,
it, it must be.
actually, if you can see the problem statement, right?
Hmm.
If you can see this particular introductory part,
Hmm.
here you
Yes,
can
sir.
see,
I got that part also. But
yeah,
if there, we have another, we have some that kind of problem where there is no, matlab, no solution like constant or balanced. Is there possibility that the measurement is except these two?
no, no. Actually, see, when
Hmm.
we are talking about the quantum algorithms, then
Hmm.
actually it is simply indicating a dedicated quantum circuit for that. So before the
Hmm.
Jozsa algorithm, there is the another algorithm, which is the basic
Hmm.
algorithm, Jozsa algorithm. So
Hmm.
their input and output and the gates are always fixed.
Okay.
When gates are always fixed, then output is also fixed actually. But that depends upon the nature of the function actually. So what is the purpose of Jozsa algorithm here? If you will understand it from the very top level, just forget
Hmm.
about the mathematics related to this algorithm. It is
Hmm.
something like for the given n number of bits,
Hmm.
given n number of bits, we have 2 to the power n different possibilities and 2 to the power n different combinations. And suppose I wanted to know whether the given function is constant or whether it is balanced, then in the classical computers, ordinary computer, I have to perform 2 to the power n number of operations I'm saying. Then I can say, okay, always the output is 0, always the output is 1. So it is constant 0 function or it is constant 1 function, something like that. But I'm saying that with the help of quantum computers, theoretically, now I'm going to show you that when we are going to apply a circuit of the Deuce Jozsa in the n number of qubits, then it is going to produce a single output 0 or 1. And from that, I'm going to conclude whether the given function is constant or balanced. So only one operation I have to perform in that particular circuit, and very quickly I can identify whether the given function is constant or balanced.
Got it, sir. Sir, is there any, my question is that, is there any possibility the number of, for the balanced condition, the number of zeros we can say that and the number of ones is equal. Is there any
Yeah,
possibility that number of zeros is greater than or number of ones is less? Matlab, is
yeah,
there any unbalanced condition is,
yes,
measurement is there? So
yes,
what's
yes,
that condition? If they
yes.
that, huh.
That particular condition is actually not addressed by the Jozsa algorithm.
Okay,
I, un-
okay, that
I
is my
got your
question.
question. Yeah, I
Okay,
got your
yes, sir.
question.
Yes.
So actually the problem statement is
Hmm.
either you can find out whether the given function is constant, or
Hmm.
you can find out whether the
Okay.
given function is
Got it,
balanced.
sir.
Like that.
Got it, sir.
Yeah.
Thank you, sir.
Madam, I also need to have one feedback that whether I should go for derivation of this circuit, or will it be comfortable, or I can talk theoretically on this actually, because
No, sir,
I'm a
both.
bit afraid.
But actually, we should grasp these things also, and derivatively is
Derivative.
also okay, and we should understand more about that. If sir, you can explain with that.
It is okay, sir.
I'm a bit afraid because yeah.
Please, sir,
You
give the
can
There,
derivation point of view also.
Yes.
okay, okay, sir.
you can give, sir.
I'm trying my best, sir. Generally, what
Just
happens
no,
is in
sir.
my
The session is very going good.
yeah, yeah. Okay, okay,
Thank you.
okay. Thank you very much. So
It's understandable, sir.
yeah,
Thank you.
thank you, sir. Thank you. So generally what happens is when we talk about any algorithm in quantum computing, we always create this kind of circuit. And for each and every operation, we are going to compute the new set of quantum state after that operation. So just like this, you can see we are starting from the qubit 0 here, right? Psi 0 actually, that is my input. So that we are starting here. And then you can see that we are going to compute the next particular thing, psi 1 after the one operation. Another operation when we are applying this particular function, we are computing psi 2. This is how progressively we are moving. And how we can solve this particular circuit is we can compute the value of each individual quantum state after the operation actually. This is how when we are reaching to the last state, quantum state, that is psi 4, then we can get the output of this particular circuit. And depending upon the output, we decide whether the given function is balanced or constant in case of Jozsa algorithm. Now let us see the input of this particular circuit first of all. So input is psi 0. So what is the value of psi 0? For the circuit input to the Jozsa, you can see 0 qubit is supplied n number of times, followed by one ancilla qubit minus. So my first state is psi 0 with 0 n number of times and qubit minus. That is my input to the algorithm. This is how we compute about the input psi 0 is quantum state. Now what we are doing after the input? After the input, my first operation is applying the Hadamard gate n number of times on the 0, right? So my psi 1, what is that? It is something like I'm going to apply Hadamard gate n number of times on the qubit, n number of times followed by the ancilla qubit minus. Now this particular expression psi 1, if you can talk about, right? So there is an expression Hadamard n number over the qubit n number of times. So now we need to derive that particular formulation. What is the generalized formula of that? So how we can write about it, right? Let us see that. So how we can write Hadamard n number of times and 0 n number of times, that we can write like this. We can say it is Hadamard n number of times, 0 n number of times. So I can say Hadamard 0, qubit 0, Hadamard qubit 0, Hadamard qubit 0. N times I have to write like this. So what is the mathematical expression of that? How we can find out the value of this particular expression in the quantum state psi 1, right? Let us simplify it. You know how quantum books, how quantum computing algorithms are dealing with it. Let us talk about this. So this expression we can write like this: Hadamard over the 0 n number of times. And as we know that when we are applying the Hadamard gate over the qubit 0, that qubit 0 becomes the qubit plus actually. So we can say it is plus 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 n number of times. Now what is the value of plus actually? A plus is nothing but it is the superposition of 0 and 1. So the value of plus is 1 by root 2 qubit 0 plus qubit 1. And that I have to write n number of times because I have n number of plus operators here. So n number of times I am writing it. Now how we can understand that when I'm doing plus 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 n number of time, then what is the simplified Boolean expression? What is the simplified expression of that? So let us see when n is equal to 2. When n is equal to 2, it means I have two Hadamard gates. I'm applying over the two number of 0 qubits. So this is how I'm writing h on qubit 0, and this is another h on qubit 0, right? So this is my plus two number of times here. And then here you can see, if I can just, open this particular brackets, then it will become 1 by root 2 square of that, because 1 by root 2 is appearing twice in this particular expression. So if it is 2 times, then it is 1 by root 2 to the power 2, and then 0 will be multiplied with 0 and 1, and 1 will be multiplied with 0 and 1. So my expression will be like this: 0 0 plus 0 1 plus 1 0 plus 1 1. And this becomes constant when n is equal to 2. So in general, I can write like this 0 0 0 1 1 0 1 1. I can say that it is one of the binary string consisting of two number of bits. So how we write this particular expression in theory of computation? We write it like this: x belongs to 0 and 1 with two number of symbols at a time, right? So it is indicating all the possibilities of the two bits of the two information which we can express. So 0 and 1 two times if I can take, then how many combinations are there? There are four combinations: 0 0 0 1 1 0 and 1 1. So this is how it is the generalized expression of that, right? It is the case when I am applying Hadamard two number of times. Now let us talk about when n is equal to 3. When n is equal to 3, Hadamard gate I am applying over the qubit 0 three number of times. In other words, I have three plus operators. So 1 plus is something like this: 1 by root 2, 0 plus 1. Another one, second one, 1 by root 2, 0 plus 1. Another one, 1 by root 2, 0 plus 1. So if we can just keep this constant value in front, we are going to get 1 by root 2 to the power 3. Then we can multiply this 0 with the remaining two bracket and these values. We are going to get this particular expression as the output. And how we can write that particular thing in the language of theory of computation? So here we can see that it is the string consisting of three elements made of 0 and 1. So x belongs to 0 and 1 consisting of three particular digits at a time, and this is how it is my generalized expression. So when n is equal to 2, when n is equal to 3, it is always the expression is coming like this. So when n is equal to n, in general, I can say that the value of Hadamard n number of times over 0 n number of times is 1 by root 2 to the power n. Then x belongs to 0 and 1 to the power n. It means the length of the string is n. It is consisting of n number of bits. When n is 3, it is 0 0 0 0 0 1. Otherwise, when in general it is n number of bits are there in one of the term actually. This is how we generalize this particular expression. Now, if you can recall our psi1, we have started from this point that we are going to apply Hadamard over the qubit 0 n number of times, then minus ancilla qubit. So now I got the generalized expression for this particular term, Hadamard over 0 n number of times. So this is my simplified mathematical expression of this, followed by minus qubit actually, right? So this I have derived the value of psi1. Now again, go back to the circuit and see that how we can compute about the psi2 from the circuit. So here you can see that in psi1 we have applied Hadamard gate n number of times over the qubit 0 n number of times. Psi2 is computed by applying the unitary function uf on the input psi1 actually. So psi1 we have computed, psi1 we have simplified mathematically. That we have simplified like this. Now I'm going to compute psi2 in my circuit. So my psi2 is simply applying this unitary function uf over the psi1. So psi1 expression is as it is in the previous equation. Now out of this, I'm just keeping this constant value in the front, and then I'm going to apply this unitary function over the input x and minus, right? So here you can see that the next particular expression, this one, are you able to see this? That uf on x and minus we are applying, right? This one. So what is the expression of that? The expression of that is minus 1 to the power fx x and minus. From where it is coming? Uf of x and minus. It is the same thing what we have seen earlier in the another slide actually, this one. When we are going to apply UF over the x and minus, we can simply express that thing with the help of minus 1 to the power fx x and minus. So from there, we are taking this particular expression, and this is how we can write UF of x and minus like this. So now we are going to replace this particular value in the psi 2. So my psi 2 will become like this. 1 by root 2 to the power n, then summation over x 0 to 1 n number of times minus 1 to the power fx x and minus. Now for rest of the computation, my minus sign is not having any significance. That becomes one of the constant value for forever. So we are going to skip that particular minus value. We are going to just delete it, omit it in rest of the algorithms. So my simplified expression for the psi 2 will become like this. So it is something like 1 by root 2 to the power n summation over x consisting of n number of string length minus 1 to the power fx and x. That is my simplified expression of psi 2. Now I have to calculate about the psi 3. How we can calculate the psi 3? So we have to again go back to the circuit. So how we can compute the psi 3? Psi 3 we can now compute with the help of psi 2, but we have to apply Hadamard gate n number of times on the first information, right? First qubit. So let us see what is the expression of psi 3 now. So psi 3, we are going to apply Hadamard n number of times over psi 2. What was psi 2? It was 1 by root 2 to the power n, then summation over x 0 to 1 n number of times minus 1 to the power of x x. So that part is there as it is. But before this, I have to apply Hadamard n number of times. Then that will become my psi 3 actually. Now this is the last part I have to derive mathematically. Yeah.
Sir, y minus is omitted there, sir. That
Hello. Hello. Am I audible, sir?
Sir, yes, sir. You are audible, sir.
Yeah.
Y minus is omitted in the above equation, sir.
Yeah,
as it is one of the input in the circuit.
And why
Yeah,
introduce?
actually, I will tell you, sir. When we are working with the quantum circuits, right? So there is a requirement of the quantum circuit that quantum circuit has to be reversible. So
Yes.
suppose my input is anything. My input can be X or anything. To make it reversible, we are adding one extra qubit to the gate, which we call it as the ancilla qubit actually, right? So ancilla qubit was minus in our circuit actually. But minus, if I can keep it also, then I'm not going to utilize minus further in my computation. It will become one kind of constant value in the further expressions actually. So for example, if we have the simple linear regression equation like y is equal to mx plus c. So
Yes,
if I can if I can omit the value of c, if c is constant, that is not going to affect much of my computation. That is not going to affect much of the relationship between y and x actually. This is
Okay.
how that c we can skip if it is not very much reused in further computations actually. So
Okay.
How
we
can we
can omit
know,
this.
sir? Excuse me.
Yeah.
So how can we know if you omit the one, if you omit the minus, how can you know the reverse order?
You can just keep it, sir. There is no problem.
Huh?
You
No.
can just
You
you
told
can
that
just
it is,
skip it. It will remain minus always at the end. You have to write minus. That's it. It will be there as it is. Y is equal to mx plus c. If c becomes constant, you can write it or not. That becomes, that is something like for simplicity, sometimes we are skipping it. That's it.
of
If you
course.
can write also, there is no problem actually.
Right.
That is simply for simplifying the expression, further mathematical expressions. We are now omitting it because it is not in use. Otherwise, if we are
For
going to
showing
use it,
reverse
we can.
order, huh?
Yeah, that at that time we can take it, sir. At
Okay.
that time we can take it if we are performing some operation. So here we reached up to psi 3 actually, right? So psi 3 is this one applying Hadamard n number of times over the psi 2. So again, I'm keeping this constant value in front, 1 by root 2 to the power n. And then here you can see this minus 1 to the power fx is as it is. Then I'm going to apply Hadamard n number of times over x because this Hadamard is shifted to the x qubit now. Now we have to calculate the value of Hadamard n number of times over the qubit x. If now we can understand about this, then entire algorithm will become very simple. Now what is x? In this expression is x is nothing but it is the string of length n, right? Earlier we have seen when Hadamard is applied 2 times, 3 times, So x becomes a string of length 2, x becomes a string of length 3, something like that. So in general, x is the string of length n, right? So how I can write x? I can write x like this, that n bits are x0, x1, x2 up to x of n minus 1. So in other words, when I'm applying Hadamard over x, I'm applying Hadamard over x0, I'm applying Hadamard over x1, I'm applying Hadamard over x2, I'm applying Hadamard over x n minus 1. So n times I'm applying Hadamard gate over the qubits, this particular individual bits belonging to x. Now we have to simplify this expression. How we are going to simplify the mathematical expression for that? So for that purpose, we need to understand the basic characteristics of Hadamard gate actually. So as I told you earlier that when we apply Hadamard over 0 like this, if we are going to apply Hadamard over 0, the output is plus. It is the plus quantum state. And what is plus? It is nothing but my 1 by root 2 0 plus 1. Mathematically, how I can write the same thing? I can write it like this: 1 by root 2 0 plus minus 1 to the power 0 qubit 1. Or when I'm applying Hadamard over 1, my output is minus. It is 0 minus 1 divided by root 2. So this I can write like this: 0 plus minus 1 to the power 1 qubit 1. So in general, when I don't know whether the qubit is 0 or 1, in general, I can write Hadamard operation like this. So Hadamard over 1 of the qubit xi is 1 by root 2 0 plus minus 1 to the power xi and then qubit 1. So if xi is 0, automatically minus 1 to the power 0 will become plus 1. If xi is 1, then automatically minus 1 to the power 1 will become minus 1. And I can get this minus as the output actually. So this is how the generalized expression of Hadamard is something like this: 1 by root 2 0 plus minus 1 to the power xi qubit 1. Now let us assume that the length of the x is 3. If we can decode the value for 3, then we can make the generalize it for value of n, any value of n, right? So what will happen when we have the 3 bits in x? In other words, the value of n is equal to 3. Hadamard we are going to apply 3 times on x. X can be written as x0, x1, x2 like this. And Hadamard we are going to apply over it. So 3 times Hadamard we have to apply. Hadamard over the x0, Hadamard over the x1, Hadamard over the x2. Now, what is the general equation of Hadamard over 1 of the qubit xi? That expression we have seen just now. That Hadamard over the xi is written like 1 by root 2, 0 plus minus 1 to the power xi qubit 1. So here we can just expand the same thing. Hadamard over x0 will become 1 by root 2, 0 plus minus 1 to the power x0 qubit 1. Hadamard over x1 is 1 by root 2, 0 plus minus 1 to the power x1 qubit 1. Hadamard over the x2, 1 by root 2, 0 plus minus 1 to the power x2 qubit 1. Now suppose we are going to expand it, right? This constant value we are keeping in front, and then remaining brackets we are opening. We are simplifying the calculation. Then this expression we are getting. So here you can see that it is minus 1 to the power x0. When it is going to multiply it with minus 1 to the power x1, then we will be having this kind of scenarios available like this. This kind of terms will come in this particular expression, right? This kind of terms will come. Now, if you can just mathematically see the pattern that what is happening. So if you can just focus on this last term 111, when the term is 111, all the 3 bits are 111. Then I have the expression available as minus 1 to the power x0, minus 1 to the power x1, and minus 1 to the power x2. When I have the term like 101, so it is indicating the presence of minus 1 to the power x0 and minus 1 to the power x2. When I have the term like this 110, it is indicating the presence of minus 1 to the power x0, minus 1 to the power x1. Last one is 0, so I don't have x2 term available there, right? So this is how now we are decoding it. And when we have this kind of expression minus 1 to the power x0, x1, then this exponent is going to be added like this. It is going to be added like this mathematically. It's very simple mathematics. So when we say it is 111, then it is becoming minus 1 to the power x0 plus x1 plus x2, because all these 3 bits are present. When it is 101, it is indicating that x0, x2 is present in the top of minus 1, and minus 1 to the power x0 plus x1. So this is my another set of qubit actually. So what is my generalized notation when I'm applying Hadamard 3 number of times over the length of 3? So that I can write like this now, right? So this I can say, this I'm writing like this. Whatever information is available 110, it is simply x dot 110. And what is that? That is bitwise addition actually. So x dot 011, it is nothing but my x0, x1, x2 bitwise addition of 011. So x0 is multiplied with 0 plus x1 is multiplied with 1 plus x2 is multiplied with 1. So this is how I'm getting x1 plus x2, right? So this x1 and x2 is simply indicating that I have the available terms 0, 1, 1. X0 was not present, x1, x2 was present. So this is how it is indicating like this. When all these three ones are available in the x dot 111, then I'll be getting this particular value as 111, x0 plus x1 plus x2. So mathematically, that particular expression is simplified, and that can be written like this now. Hadamard n number of times over the qubit x can be written as like this: 1 by root 2 x belongs to the length n 0 and 1 minus 1 to the power x dot z with the qubit z, right? That is the common expression. If you are getting it a bit faster, or if you are not able to understand any immediate state, I'll share it later on actually, right? Because I think it is already 6:56, and in the remaining 30-40 minutes I have to cover another algorithm also. So don't worry about this expression as of now. Now you can assume that that expression is simplified like this. Now let us see next operation what we are going to do. So before this we have to compute the psi3 value. So psi3 will be calculated like this from the psi2 with the simplified expression like this, right? And then out of this Hadamard we are applying n number of times, so my expression will become like this,
Where?
right? Now next is we have to compute the last output of the algorithm, right? We have to compute about the psi4 at the end from the measurement. So now there is no gate, only measurement is there. So we are going to fix some value, and then we are going to check the output actually from the psi3. So my psi3 calculated and simplified was this one. Psi3, the final value calculated was 1 by to the power n, x belongs to 0 to 1 n length minus 1 to the power fs plus x dot z qubit z, right? That is coming from the previous term actually. So now let us see that my given input was all zeros actually. When I'm saying that my given x is 0, 0, 0, all bits are 0. If I can put that particular value in this expression, then that will become the simplified expression like this, right? Because I'm going to multiply x with all the zeros like this. So that will compute the remaining expression like 0. My simplified expression will be this, right? So what will happen if my f is constant? If my f is constant and I'm going to just add it up, then what will happen is either f will be 0 or it will be 1. So that term will come to 2 to the power n number of times. And that is going to be divided by 1 to the power 2 to the power n. So that will become 1. So if my output is 1, right, for all zeros, then I can say that my function is constant. If it is -1, I can say it is constant 1 function. So when I'm checking the amplitude of all zeros, and suppose I'm getting the output as plus or -1, then I can very much declare from the one operation only that my function is the constant function. It is either 0 constant or 1 constant function, right? Otherwise, I can say here that my function is balanced if the output of the algorithm is 0. Because what will happen is for half of the expression, it will become, -1, and for half of the expression, it will become +1. It is balanced, so half input is -1, half input is +1. If I can just sum it up, it will automatically become 0. So amplitude of 0, 0, 0 will become 0. So by simply looking at the measurement, if output is 0, quickly I can say it is balanced. If output is plus or -1, then I can say very much it is constant. So from single operation only, we can decide about this particular problem. This is the overview of Jozsa algorithm mathematically. It is a quite older algorithm of quantum computing, and that is expressing the power of quantum computers, that the algorithm which can take 2 to the power n number of operations in our ordinary laptop, ordinary computer, ordinary GPU, that can be solved with the help of only one operation of Jozsa circuit actually. So that is our first algorithm, which is called as the Jozsa algorithm. Now, second algorithm I have been assigned is for this particular FDP is Grover search algorithm. There are several ways by which this particular algorithm can be implemented. So we are going to talk about the important steps, that how we can implement those particular steps and we can identify one of the element. So Grover search, as the name is indicating, it is one kind of searching algorithm, right? It is something like searching a particular telephone number in the telephone directory. So what happens is, in our classical computers, we have various searching algorithms. And the best known searching algorithms is something like log of and base 2. And even for that, there is a requirement that the number has to be sorted. For unsorted, databases, at least n number of search operations are required. Whereas, if we can talk about the Grover search algorithm, the best complexity known is order of root of n. So if 100 records are there, and root of 100 is 10. By only doing 10 operations, we can very easily search one of the element available in the databases. And in which year it was proposed? Look at this. Quantum computing is new for us, but theoretically it is one of the very older technology because it was derived from the quantum mechanics. So here you can see the scientist Grover. He has invented this particular algorithm in 1996. Around 30 years ago, this particular algorithm was proposed in one of the research paper actually, right? So let us see the working of it, and we can very much simplify this. So any quantum algorithm, as I told you, that can be simplified like a quantum circuit. So here you can see that we have the databases input X, we have the ancilla bit, and then by applying a unitary function, we can perform the search operation on it. But how searching is done? Let us see, right? It is the general circuit diagram. Grover search algorithm. Suppose I am searching for any element A in the given databases. So function will compute f of A as 1 for the given search element. If it is present, then function of A is the search element. F of A will compute the output as 1. If that value is not present, for remaining values, the function will calculate 0. If I'm getting the value 1, it means that element is present in the databases. And that we can identify in the order of root of n actually. This is how it is very faster algorithm, right? So here you can see that graphically what we can show it here, like we have the length of n number of elements. If the element is present somewhere, then that is flipped to 1, right? And remaining elements will be flipped to 0 because that is non-required elements actually. So let us see the block diagram of it. This is one of the iteration of Grover search algorithm. So here you can see we are having input, we are having Hadamard gate, then we have unitary function, some different functions we are applying. It is called as the single Grover iteration. And friends, one of the interesting thing is there are so many possible Grover search circuits actually. It is not only the one. By devising your own circuits, you can implement Grover search algorithm, but you have to remember about the important operations of. So what are the operations you need to implement if you are creating circuit by your own? So the first operation is the initialize. You have initialized the data like this, which is the unsorted data. So it is simply indicating all the pipes are indicating the presence of the information in the databases. Then the second one is the you have to develop a devise a function with the help of Grover search logic. You have to devise the function, and there are several ways by which you can devise the function, right? So what will be the objective of function? The objective of function will be something like whatever search element is there, you have to simply shift that particular element so that that can be differentiable from the others like this. And the third operation is something like you have to go for the amplification of that. Once we have identified that that is my search element, then we have to keep increase the amplitude of that particular information so that very easily we can identify it. And at the end, when the Grover search algorithm is completing, finally that will become 1 and remaining all will become 0 actually. Till that time, we have to proceed like this. This operations we have to perform. And let us talk about this particular thing, that how we can phase shift it and how we can amplify the amount of information here, right? So let us talk about this now. This is the overall picture of the operations of the Grover search algorithm. We have to initialize, we have to apply some oracle function to shift the value search element, then we have to amplify the search element, and this thing we have to repeat. How many times we have to repeat? We have to repeat it root of n number of times, and then only my search element will become 1, remaining elements will become 0, and very easily I can identify a particular item in the databases. It is a bit of more theory related to it. It is the picture of the scientist who invented it. He was Indian actually. In 1996, he has proposed this particular algorithm, right? This far, far away. We are learning it today, but it was proposed 30 years back. So I'll talk some of the key things related to it actually, right? So as I told you that if you have 100 number of elements, then only 10 circuit runs are required. And very easily you can identify that particular thing. Now this slide is important about the amplitude amplification. How we can amplify one of the quantum information in the quantum state. So if you can see this particular diagram, we have the quantum state psi, which is consisting of the equal probabilities for different values. 0, 0, 0, 1, 1, 0, 1, 1, all is having the multiplication coefficient of 1 by 2. Or in other words, the probability of all the 4 elements in the 2 qubit system 0, 0, 0, 1, 1, 0, 1, 1 is 25%. How we compute the probability? That is the square of the multiplication coefficient, right? Alpha 0, beta 1 we are saying. So probability of 0 is alpha square and probability of 1 is beta square. So 1 by 2 square if you will do, you will get 1 by 4. So 1 by 4 is your 25% probability. So 25% probability for 0, 25% for 1. So it is equally distributed information as of now. Suppose 1, 1 is my search element, right? The last one. And I need to enhance the amplitude of it. So that is indicating one possible way by which the amplitude can be enhanced. So my modified quantum state is 1 by root 12 0 0, 1 by root 12 0 1, 1 by root 12 1 0, and root 3 by 2 1 1. Now what is the probability of 1 1? It is square of root 3 by 2. So that is my 3 by 4. 75% amplification, 75% amplitude value is there for 1 1. Earlier it was only 25%. For remaining 25% is divided for the remaining 3 information. That is 1 by 12 actually, right? So around 8 point something probability is there for the 0 0 0 1 1 0. So mathematically how this amplitude amplification is done, again there are several ways. So one of the several ways is indicated in this particular diagram, right? So what we are doing is we are simply saying that start with the balanced superposition. All the probability values are equal. And we have to identify what is our search element that is input to the algorithm. And then we are simply applying the phase flip to the search element like this. So after applying the phase flip, my search element will become on the bottom. 1 1 is the search element in this example. And after this, you can see it is my amplitude amplification procedure. So initially the probability is same. So I need to compute the average of the probability values. Then
Excuse me,
from
sir.
half of the, yes.
Sir, a little curiosity.
Yeah.
When we start hunting for this 1 1 element, how we started, I mean, how we could guess it that we have to flip this 1 1?
Actually, sir, if you can see the working of this algorithm, Grover search algorithm is one kind of search algorithm. Whenever we have the search algorithm, so we are providing the input which is required to be searched in the given database T, right? So that element we have to search in the database. Search element is given as the input to the algorithm. I am already telling the Grover search algorithm that out of the available information, I have to search about 1 1 for the simplicity. In general, there are 1 million records, so I can specify search the record of this particular account number. So that account number I'm supplying as one of the search key for my searching algorithm. So 1 1 is supplied as the input to the algorithm here actually.
Got it. Thank you.
Yeah. So here you can see that we are calculating the average of the probability values, and then we are simply applying the mathematical trick, that is invert all probability amplitudes about the mean. So mean values, whatever is there, by that amount of information we are applying to the search element, and we are increasing the amplitude of that till we are getting the final amplitude as 1 for the search element and 0 for the remaining elements. So this is how, in general, this particular algorithm is working, and that is also called as the diffusion operator actually, right? So Oracle is flipping the desired search element, diffusion operator is increasing the amplitude about the mean. So these are the two primary operations we are performing on the Grover search algorithm, and this thing we have to repeat root of n number of times, then only we can find out our search element in the databases, right? So this is one possible circuit of the Grover search algorithm. You can see Hadamard we are applying to the 0 0 0 qubits, and then we have the two functions, Oracle function and diffusion operator, and then we are getting the output. It is again a repetition of the same thing, but one slide is important out of it that I wanted to discuss in this algorithm. It is the same thing. It is saying same thing. Identify your search problem, apply it root of n number of times, this that. But one thing is important in this, and that is, yes, this one. This slide is really important for Grover search algorithm. If you can read the line number 1 of this slide, it is saying that there are a few ways to implement for the Grover's algorithm F, but the mechanism for the search process stays the same actually. So diffusion operator will be there, and then that facelift operator will be there, but circuit creation possibilities are different actually. There are so many ways by which the same algorithm can be implemented in the quantum computing. It is just like we have different ways, we have different loops available in our classical computers by which we can perform the same operation actually. So Grover search is also saying that there are many possibilities of the circuit, and you can design the circuit by your own. But the key thing is you have to always follow the same procedure, standard procedure, what is mentioned in the Grover search algorithm. And there are ways by which, the Grover search efficiency can be increased, right? So it is something like we searched one item at a time, but it is possible that you can search in the multiple databases, you can search multiple values at the same time. That is possible. By doing some manipulation in the circuit, we can achieve that kind of implementation. Right. And then the last point is important. As of now, we have not shifted entirely to the quantum computers. So we are interested to develop the hybrid quantum computers where partial implementation is done in the classical computers, partial information implementation is done in the quantum computers. That kind of circuit, if we can, devise, then partial implementation of Grover search we can do. That is even again possible. So that is all about the theoretical aspect of both of these algorithms. Now I'm going to talk about a bit on the implementation actually. So today there are a lot of APIs, a lot of things available for implementation of the algorithms, but I prefer the most simple way by it can be implemented. Qiskit and Pennylen, these are the two popular APIs to implement any kind of algorithms related to the quantum computing. And the fantastic thing is both of these APIs, both of these technologies are actually also available on the Google Colab. So in the Google Colab, I'm not explaining you the detailed code of it, but I can show you that, how it can be implemented in that. So it is one of the way by which it is implemented in Google Colab. So first talk about the Jozsa algorithm. So here you can see if you are going to work with the Google Colab, first of all, you need to install about the Qiskit. It is the Qiskit implementation of both of the algorithms. So like this, it is one of the Python-based API. So in Google Colab, you can very well say that you have to install the libraries Qiskit and Qiskit Air. Qiskit Air is the actually compiler and simulator of the quantum computer that you need to first of all install. Then you have to install the relevant libraries related to that. And then you can check whether the given version was installed in your Google Colab environment or not. So suppose it is it is available in your environment, it will be printing the version names of both Qiskit and Qiskit Air. And then you have to implement about the function, use Jozsa algorithm. It is one of the way actually. So it is n qubit. So here you can see the definition, the function definition in the Python. So it is taking an input as one of the thing, right? One of the input parameter it is taking. So that is simply indicating that it is n qubit gate actually, right? So that is one of the parameter, and we can specify while calling this particular function. So here you have the logic related to it, but before that you have to create the circuit, quantum circuit of it. So that we are going to do in the next slide. Here you can see it is the algorithm. It is calling quantum circuit n plus 1 comma n. Here you can see the possibility of applying the Hadamard gate and number of time x. And then here you can see use Jozsa oracle, and we are supplying the value of n. And then finally we are creating circuit of it. And finally, if you can recall, the last operation was measurement. So that kind of thing we can implement. And here it is the case study related to that. Simulator we are initializing, and then circuit we are initializing. This is the code related to it. Circuit we can print also, and then we can supply the input also, and then we can find out whether it is working or not, right? So here you can see if you can just apply it, then it can create circuit like this. It is for the 3 number of qubits, and then it is saying it is constant or balanced or something like that. That is the first implementation. Another one interesting one, Grover search algorithm. Here you can see we are going to apply the Qiskit API first of all, and then we are simply importing the same libraries from the Qiskit just like that. Then we are going to create the bit string out of it. And then there are operations, if you can recall, diffusion, amplitude amplification. This is diffusion with the help of gates and all that, right? And then we are going to specify about the target search element. That is 101 in this particular case. And we are specifying the value of n and all that. So here it is simulator one, and it is identifying one of the output actually. I'm not explaining line by line this particular code. So here you can see we are able to draw the Grover search circuit. And if you can see the output, it is something like this. It is for the search element 101. It is almost becoming, higher as compared to the other one. And down the line, you can also print the frequency of it actually. This is how we can search 101 in the given Grover search algorithm actually. So the key takeaway of this particular talk is, whenever we are going to understand any particular quantum algorithm, so we need to understand about the quantum circuit related to it actually. And for understanding the quantum circuit, we need to understand what are the important quantum gates which are required for that, right? And then there are many ways by which the same circuit can be drawn. That is also there. So when we are implementing this Grover search in Pennylen or in Qiskit, again, there are possibilities that there are 15, 20 different ways by which the same program can be written. And I'm able to get the output like this actually. These days, we have a lot of simply, Google Colab kind of platforms very easily without installing anything on my system. Directly with the help of internet, we can implement these things and we can have outputs of the required algorithms actually. So friends, my only point is, if you are really serious about developing your own algorithm or trying any algorithm related to Deutsch Jozsa or something like this, you always start by understanding of the circuit, right? And actually there is a prerequisite to Deutsch Jozsa algorithm, and that is Deutsch algorithm. That is simple one as compared to the Deutsch Jozsa, because that is 1 qubit input, 1 qubit output. Here we have seen the complicated one, n qubit input and 1 qubit output. Therefore, we have seen a lot of mathematical derivations. There the mathematical derivation is simple. The only thing is, this circuit we have to design, the gates we have to understand what gates we are going to utilize, and how we are generating the output, how we are going to decide about a particular problem. What is the purpose of both of these algorithms? Algorithm number one is indicating that by doing only a single operation in my quantum algorithm, I'm able to decide for the given n number of qubits whether the given function is balanced or constant. Whereas 2 to the power n operations are required in my classical computers. So if n is equal to 10, if number of bits are 10, 1024 operations are required in the ordinary computer. Whereas only one operation is required in the quantum computers. So this is how quantum computers works very fastly as compared to the classical computers. If we can talk about the searching problems like Grover search. So if 10,000 elements are there, and I can apply best of the algorithms of classical computers. So many hundreds of operations are required. Whereas root of 10,000, only 100 operations are required in case of classical computers, because the time complexity is root of n actually. Again, that is showing the another exponential power of the quantum computers. So those are the benefits, standard benchmark algorithms to demonstrate theoretically that what is the primary benefit of both of these algorithms. So now we are open for any kind of discussions or any doubts or anything you wanted to discuss more on this. But before going for discussion, I will tell you one more interesting thing that these days we are talking about implementation of AI in quantum computers. So we have artificial neural network, we have CNN implementation in the quantum computers. So for them, actually, there are few other dedicated quantum gates, like rotational gates are there. So rotational gates are actually derived out of the Bloch sphere, which is the graphical picturization of the qubit actually. So there we are supplying the angle and we are rotating the quantum information. So this is how rotational gates we can deploy very easily, and we can implement any of the artificial neural network very easily in the quantum computers and quantum simulators actually. If you wanted to discuss anything, we can talk about that.
Session is open for questions. Anyone having any questions, you can ask, sir. Am I audible?
Yes,
Yeah,
sir.
yeah.
No query, sir.
You are audible, sir. It is clear, sir. Thank you.
Sir, thank you very much for your informative session.
Yeah, sir,
Especially,
just one thing I wanted to ask to the audience, that whether any faculty is teaching this subject, quantum computing, in their colleges.
Not right now, sir.
Sir,
Okay, okay,
actually, from the next academic year onwards, we are going to start it, sir.
Sir, actually,
okay,
maybe this is not in Abhi academics part. It is only in research, more in research part right now. It's not in,
okay, okay.
yes.
Got it.
It has
sir,
been
we are
kept here, sir. In this semester, we are going to teach that one.
Okay, okay, great.
Sir, next time, next semester onwards, we have to move the minus course, sir, for this.
Actually, the fantastic thing is, like, sir, Government of India has launched that National Quantum Mission, and they have a very huge budget, 6,000 thousand crore rupees budget in that particular mission. And apart from that, lot of development is going on in the Amravati area actually, because most of the newer IT companies, in fact, IBM, they are going to set up their own quantum computer in Amravati Quantum Valley. So Amravati, they are setting up as the first quantum valley of India actually. So there, in fact, one of the 4-qubit quantum computer is already deployed by one of the startup company of India, Sai Phi, something like that. They have deployed it actually. So very soon we can see, a lot of development in this particular domain. And over the period of time, I think that it is going to bypass our GPUs and traditional way of computing.
Sir, I have one question, sir.
Yeah, yes, madam.
Good evening, sir.
Yeah, good evening.
First of all, I would like to thank you for your very nice explanation of both algorithm.
Yeah,
Sir,
yeah, thank you,
sir,
madam.
I have one query related to, is there any possible to develop any API for IoT?
Madam, actually, see, if you have any API related to IoT in Python, then
Yeah.
you have the Python API for quantum computing also. Like you have Pennylan in Python, you have Qiskit in Python. So in the Google Colab, you can import all the APIs, API of IoT, API of quantum, and then possibly you can integrate both of these APIs. So integration is possible in the simulation part actually. The fantastic part is, as of now, in most of the APIs of quantum computing, they are actually created in the Python. And people are very much, familiar with the Python, particularly in the data science kind of projects. So it is very easy to integrate quantum computing with data science kind of projects. First of all, AI, ML, IoT, we can do it.
Okay, sir.
Sir, am I audible? Hello?
Yeah, yes, madam, yes.
Sir, uh, how many techniques are available to store the quantum images? Means, is there any famous technique to have quantum image representation?
Madam, actually, that is a difficult question, I can say, because once we talk about the quantum information, right? I
Okay.
think you have a dedicated session on quantum machine learning also, and one professor from my institute, Professor Kapil Soni, is going to talk about that. So there are data encoding techniques in quantum computing actually,
Okay.
and today there are at least 15-20 different standard benchmark data encoding techniques.
Okay.
So data encoding technique is something like how we are going to map our classical information to the quantum information.
Quantum fit. Yes.
Right? So whatever quantum information I have, how I can represent that quantum information in terms of the qubits. That is the process. So what is happening is I have some benchmark encoding techniques. Apart from that, even one of my PhD scholar, he is devising his own way of data encoding to the quantum computers. So this is how we can devise our own also. That is possible.
Okay, sir. Thanks.
Sir, can you help us in suggesting a book which starts from very basic and then gradually goes up in quantum studies? Am I audible, sir?
yes, sir, you are audible.
Yeah, actually there is power off at my end actually. Hello.
Yes, sir, you are audible, sir. Sir, you are audible.
Yeah, sir, the book of Nielsen is very standard one for quantum information, quantum you can always start with that book. That is standard textbooks in the domain of quantum computing actually. And then there are so many other books on quantum machine learning, data encoding, this and that. So always start with the book of Nielsen, because that will give you the fundamentals of quantum computing actually.
Right, sir. Thank you.
Sir, I have one query, sir.
Yeah.
Sir, in the initial days of quantum computing, I thought that quantum computer doesn't require any processor because the subatomic particles continuously emitting the frequencies like electrons, protons, those frequencies will utilize the process to process the information. But nowadays, the reality of the quantum computer, it also required a quantum processor. Is there any specific thing, sir? Sir, does my question is clear to you, sir? Hello.
I think.
Hello.
Yeah.
Actually, there is power off at my end actually. So sorry for the disturbance. Yes, sir. Please continue with your question.
Sir, in the initial days, what we thought is quantum computer doesn't require any specific processor to process the information because the hardware component of the computer itself is subatomic particles using these are continuously emitting the frequencies and energies. With the help of those frequencies and energies, we can process the information. But what the real quantum computer existing, it also needs a quantum processor. Am I right,
yes,
sir?
Yes, sir. Correct. Actually, this is how, there is another domain of research about the quantum hardware devices, quantum memory, quantum processing unit and all that. And if you can see the National Quantum Mission, one of the objective is related to it actually, quantum hardwares. And that is I can say that is the biggest challenging area to that particular mission, because we Indians are very good in coding, algorithms, computing side, software development and all that. But hardware designing and devising our own integrated circuits for newer computing things is a really challenging area actually. And that is closely tied up with semiconductor design mission of government. And they are therefore putting a lot of money that how we can manufacture our own ICs, our own semiconductor devices, our own hardware things related to the systems. But I think, sir, I'm hopeful that over the period of time it will be there. Slowly some research will be there. I was talking about Kapil sir, so his PhD area was related to quantum memory management. So memory devices, RAM, quantum RAM, he has worked with. And slowly people are also concentrating in that area, and possibly some good solutions will come up in the future.
Thank you, sir. Thank you so much.
Any more questions?
Sir, good evening, sir.
Yeah, madam, good evening.
Hello. Good
Yeah,
evening,
yes,
sir.
madam. Good evening.
Sir, I have a question, sir.
Yeah, yes, madam. Please.
As quantum computing is having one of the important property as quantum entanglement. So,
yes,
regarding quantum cryptography, what is the security feature if I'm using this quantum cryptography for entanglement, sir? Can I have a security enhancement protocol design for this, sir?
Madam, that is a really good actually question. And there is a technology, there is a set of technologies in the domain of quantum computing, which is called as the PQC. That is called as the post-quantum cryptography. So
okay,
I think very soon you are going to study about the Shor's factorization algorithm in one of your session. So that says that the moment quantum computers will exist and very easily they can crack the bigger prime numbers, which we are going to utilize in case of RSA algorithm. So our entire security systems will go into the hell actually, and very easily the security can be breached with the help of the quantum computers. So is there any security mechanism which can be enhanced even after the existence of the quantum computers? So that particular set of technologies is called as the post-quantum cryptography. So that is something like maintaining the security even after the existence of the quantum computers. So for that purpose, if you can see, then now people are trying to develop the new security algorithms by incorporating all those basic quantum properties, quantum entanglement, quantum superposition, quantum gates, rotational gates, and mixing up of the information, encoding techniques, by which the better security algorithms can be developed. So this is how, if you are interested in that domain, then try to study about that particular part, PQC, post-quantum cryptography. That will give you the bunch of newer technologies and answer related to your question actually.
Okay, sir. Thank you. Thank you, sir.
Naresh,
you
sir,
very
am
much.
I audible?
Yeah, yes, madam.
Sir, last question.
Yeah.
Sir,
Okay, ma'am.
when we implement, hello?
Yeah,
Okay, ma'am.
please continue.
Yes, sir, when we implement any method or any technique in quantum simulation software, so till now, I only find 3 performance parameter, like number of qubits or circuit structure, space or time complexity. So is there any another parameter? Because it is my research area, quantum image representation. So if you guide.
Madam, possibly you might be using some neural networks for your work, I suppose.
Yes, yes. Qiskit
Yeah, so
lab
what?
and.
Yeah, I got it.
Huh.
So what happens is when you are implementing the neural networks, then as I told you that you need to have the rotational gates in place, right? So
Okay.
when we are working with the rotational gates, then angle parameter, theta parameter becomes one of the hyper parameter for your algorithms. So the way we are doing research in case of deep learning, when we are where we are saying that we have the learning rate as one of the hyper parameter for our deep learning algorithm, or we are saying that for LSTM, these are my gates and these are the parameters related to the input output gate of LSTM, something like that. So there we are focusing on the hyper parameters. What is my learning rate? What the number of epochs is required? Whether Atom optimizer is taking beta 1, beta 2 values? What are the suitable values of it? So likewise, for quantum computers neural network, we can focus on the angle values actually. What are the different possible angle values in the rotational gates which will optimize the result of my algorithm? That kind of work can be taken up actually. That is called as the hyperparameter tuning in neural network for quantum computers. Rotational gates and properties of rotational gates you can explore for the different possible values. Or you can
All right,
optimize it
sir.
with the help of some optimizers you can apply actually. Very well, you can apply any of the existing optimizer algorithm to the rotational gates, which will optimize the better suitable angle values for your neural network.
Sir, is hybridization is quite suitable when
Yeah,
we merge two techniques?
as of now, most of the algorithms are hybrid in nature. So some part is executed in the classical way, classical computers, and some part is given to the actual quantum computers or quantum simulators. So that is the best way actually. These days, most of the research work is going on in that particular direction also. Over the period of time, it will completely become the fully quantum implementation. But as of now, most of the implementations are hybrid in nature.
All right, sir. Thank you so much.
Thank you.
Thank you, sir. Thank you, sir. Thank you very much for your insightful session. We are very much thankful for you. Thank you, sir.
Thank you, sir.
Very much.
Thank you, sir. Thank you, everyone, for giving time and listening. And I wish all the best to all the participants. And I hope that this FDP will be very much, useful, and you will be taking a lot of things from this particular FDP. So all the best, all of you, and good night. Thank you.
Thank you, sir. Dear participants, already our next presenter was joined, but for the sake of recording, I will pause for a few minutes and again we will continue so that we can have 2 separate videos for easily learning. Please be in the session only.